Hi everyone. In today's video, we will cover Composite Great Circle Sailing. Before I do a numerical or a question, I want to talk a little bit about the theory behind Composite Great Circle Sailing and what it is. So let's first start with what is a rhumb line and what is the difference between a rhumb line and a great circle. Alright, so when we did Mercator Sailing, remember I mentioned Mercator Sailing is based on rhumb line sailing. Now rhumb line sailing is what is rhumb line sailing is that we have Mercator charts where the meridians are parallel and perpendicular and equidistant placed, right? So a rhumb line can be drawn across these meridians on a Mercator chart and it comes across as a straight line. So a rhumb line courses can be drawn as straight lines on Mercator charts. They are also the shortest distance between 2 points if we talk about, let's say if we talk about Mercator sailing. Now why I'm saying if we talk about Mercator sailing, because the definition of a great circle is also that a great circle is the shortest distance between 2 points. So what is the difference between a rhumb line and a great circle? So remember that rhumb line courses and great circle courses on a north-south component. If you are going north to south or south to north, the difference between rhumb line courses and great circle courses is not much. The distance will be pretty much the same. But if the more the curvature of the earth comes into account, sailing on a rhumb line course, which is drawn as a straight line on the Mercator chart, will no longer be the shortest distance because you will have to take into account the curvature of the earth. So therefore, rhumb line courses are good for Mercator sailing, but the more curvature of the earth comes into play, it is better to engage in great circle sailing, which takes into account the curvature of the earth and becomes the shortest distance between 2 points if drawn like an arc. But if I draw an arc on a Mercator chart, I cannot sail. How can I sail along an arc? I can only sail on straight lines. Therefore, great circle sailing is based on sailing on mnemonic charts. Mnemonic charts. Now, what are mnemonic charts? Mnemonic charts accurately describe how the globe looks like. So this is how the meridians are drawn on a mnemonic chart, and the latitudes also come across as curved lines. But I cannot use mnemonic charts for sailing because I cannot measure my latitudes. My longitudes are not equidistant placed. The latitudes are not like that. I cannot use it. So mnemonic charts are normally small scale charts, I should say. So they cover large parts of the world in one single chart, small scale charts. All right. So on a great circle or a mnemonic chart, when I draw a great circle, it comes across as a straight line. Great circle comes across as a straight line. The same great circle, if I draw on the Mercator chart, will come across as a curve. Similarly, if I draw a rhumb line on the Mercator chart, it comes across as a straight line, but the same rhumb line, if I draw on the mnemonic chart, will come as a curve. Which means I can either sail on mnemonic charts using great circle or Mercator charts using rhumb line sailing. Like I said, the difference in the distances is not much in the north-south component, but as and when the more the curvature of the earth comes into play, the great circle courses become the shortest distance. But if I draw great circle as curves on Mercator charts, I can't sail. So what is the solution here? So what we normally do is we draw great circle courses on mnemonic charts, just like the red line on your right side, and we find the shortest distance between 2 points, and then at every 5 degrees of longitude, we note down the waypoints. And we transfer this onto the Mercator chart for every 5 degrees of longitude and try to find the shortest way across the 2 ports or 2 destinations. So on the Mercator chart, a rhumb line or course is drawn as a straight line, of course, but a great circle course will not come exactly as a straight line. it will not come exactly as a straight line. So a great circle course may sometimes come like this, because you are converting a curve into a straight line, right? So this is Mercator chart, and you have converted a great circle course into a rhumb line course. So once you draw the great circle course on a Mercator chart, what you can do is, then looking at the navigational features and the navigational hazards, you try to modify this and try to make it as straight as possible as you can, and see that you get the shortest distance between the 2 points. So you draw the course first on the great circle, and then for every 5 degrees of longitude you note down the waypoint and then transfer it onto the Mercator chart. Mercator charts are also large in numbers. They are available as large scale charts and small scale charts. Gnomonic charts, not so much. They are much lesser in number. They are mainly small scale charts, and you use them to draw the courses or the shortest courses between 2 points and then transfer it to the Mercator charts. If you are doing the ECDIS course and you do a comparison, you will see that for most of the courses, the great circle courses will be shorter distance than rhumb line, but except on the north-south courses. So if you are going exactly north to south or south to north, you will see not much difference between these courses. Another problem with great circle courses is, because it's a small scale chart, sometimes it takes us into high latitudes. Now taking us into high latitudes would mean that you may run into bad weather. Some compass will not behave the way you want it to. So magnetic compass especially has issues, especially north of 70 degrees or 70 degrees south of 70 degrees. The magnetic compass may sometimes go a bit awry and you cannot rely on it. Olden days gyro compasses used to behave strangely as well, but nowadays no. Fiber optic gyros are very accurate, so you have no issues with fiber optic gyros. So many masters these days do go into higher latitudes. That's why you are also learning high latitude navigation, I'm sure, as part of your course. But sometimes some masters tend to avoid going into higher latitudes, and that is why this is another disadvantage of a great circle sailing, and people prefer to sail on Mercator sailing or rhumb line sailing. Now what happens if you go into higher latitudes is, sometimes masters will say that do not take me north or south of a certain latitude. So in that point of time, what you normally do is, you can come up, let's say you are going on a great circle course from point A to point B, and because it's an arc, it will go like this. Okay, it doesn't go like a straight line as you would imagine, because we have to take into account the curvature of the earth. Now because this latitude here may be a very high latitude which the master is not comfortable with, what the master will ask the second officer is, maybe you come up to here, do a parallel sailing, and then resume the course at this point. So that means here you are doing a parallel sailing and then resuming the course going back to B. This is called composite great circle sailing, where we set a limiting latitude. What is a limiting latitude? That is the latitude up to which we can go up to, and then do a parallel sailing and then resume our voyage, so that we don't go north or south of a certain latitude, which is up to the discretion of the master. There is no limiting latitude value that I recommend. Like I said, more and more ships these days are going into higher latitudes, and high latitude navigation is taking place. That's because it's the shortest course, and companies like ships to reach early, save on fuel, take the shortest course as long as it is the safest course. Alright, so today this is what we'll be doing. So let's get into the math of it. Today I will do one question, and in my next video I will do another question. So in today's question, we have two positions, and you have to find the composite great circle distance between two positions. So position A, or the departure position, is 37 degrees 48 minutes north, 1 to 2 degrees 40 minutes west, and position B is 35 degrees 40 minutes north, 141 degrees 0 minutes east. The limiting latitude that has been set, you cannot go north of this latitude, is 45 degrees north. Alright, so there are few steps that we follow here before you start doing the question. You have to first draw a diagram. Alright, you draw a diagram. So to draw a diagram, what you do is, first look at the two latitudes. If both latitudes are north, you will draw it with respect to the north pole. If both latitudes are south, you draw it with respect to the south pole. If one is north and the other is south, then you will look at the latitude which has a higher value and draw the pole accordingly. So if you had 40 degrees north and 60 degrees south, you would draw the south pole because the value of the south latitude was higher. However, in this case, both are north, so you will draw it with respect to the north pole. So I draw it as north pole, so I will draw north pole here, and then I will draw the two positions. So I will go from P. So hopefully on the side you figure it out where will be A. So according to me, A will be here at 37 degrees north, and B will be slightly south of it at 35 degrees north. Now why is A on my left hand side, although I think it should be the other way around, because our west should be, so I will just change it, sorry. So see, this is how you correct yourself. So you also have to look at the longitudes, you can't only look at the latitudes. So A will go slightly there you go. So A will go on my right side. I will explain why. So although A is 37 degrees 48 minutes north, remember your longitude is 122 degrees 40 minutes west. That means, and I will show you later on what I mean, you have to find the shortest D long as well. Okay, we'll come to this later, that how I determined. So what you do is the next step. So first step was looking at the two latitudes and determining the pole. The next step is looking at the two longitudes and finding the D long. So in this case, angle P in the triangle becomes your D long because it is suspended between two meridians, meridian of A and meridian of B. And how do I find the D long? Same names, subtract, different names, add. So longitude A is 122 40 minutes west and longitude B is 141 degrees 00 minutes east. So different names, if I add the two, what do I get? 40 minutes, and then this will be 263 degrees, and I'm going from west to east. That means I'm going easterly. But D long cannot be greater than 180 degrees. That means this is incorrect, right? It cannot be greater than 180. So I will subtract it from 360. I will subtract it from 360 degrees. And what do I get? Let me do it on my calculator. 360 degrees minus 263 degrees, 40 minutes. I get 96 degrees, 20 minutes. And I reverse the direction. I make it west. So that means I am close to the anti-meridian. So if I am west, I will come on the right side. And if I am east, I will come on the left side. Oh, sorry. This is B and this is A. So B is 35 degrees 40 minutes north, slightly lower of A, and 141 degrees 00 minutes east because I am close to the anti-meridian. Alright, so this angle P becomes my D long, 96 degrees 20 minutes. Then I draw the limiting latitude. So I have to draw arcs. Remember, in this type of a question, you don't draw straight lines, you draw arcs. So you go here, maybe. So remember, your limiting latitude is 45 degrees. So it should be north of both A and B, and then here. So I will assume that this is 45 degrees and I will join this with P. Sorry, this should be joined. And I will call these vertices VW. And this is 45 degrees north. Now what is vertex? A vertex. A vertex is the highest point of the great circle arc. So this is a vertex. If you go by the definition of a great circle, equator is a great circle, the meridians are great circles, they divide the sphere into exactly two equal halves. But every arc has the highest point, and at that highest point you will see that if I draw an arc like this becomes the highest point, and at this point you can see that it's pretty much a straight line. That is why VW, which are the vertices here, or vertex, or plural of vertex is vertices, they become a straight line. That is the only straight line you draw in the diagram, nowhere else. Rest of the diagram should be drawn as arcs. Alright. So once you have done that, this becomes the vertex always subtend the 90-degree angle. Also they are kind of parallel sailing, so it becomes 90-degree. All right, and then we start labeling our diagram. So first we label PA. So let me just erase this. If you have noted it down, just let me erase this as well so that it doesn't become too cluttered. So PA means from the North Pole to the latitude, right? From the North Pole to the latitude. How can we find that out? So because we know our latitude already, so in this case, let me just show you. So when I say latitude, what do I mean by latitude? So if this is equator, from equator to A is my latitude, which is 37 degrees 48 minutes north in this case, right? But from my pole to the equator, how much is it? From pole to the equator. From the pole to the equator is 90 degrees. So PA, this here would be PA would be 90 degrees minus 37 degrees 48 minutes, which is equal to 52 degrees 12 minutes. And PB would be equal to similarly 90 degrees minus 35 degrees 40 minutes, which makes it 54 degrees 20 minutes. And I know my angle P already, right? Is there anything else I know? I know PV because the latitude of vertex is 45 degrees north. So PV will be 90 minus 45 degrees, and PW will be 45 degrees as well. Again, because the latitude of PV and PW is 45 degrees, so this is 45 degrees from the equator. Remember, if your B was below the equator, you would add 90 to the latitude of B. Alright, so if any time you have a latitude in the north and a latitude in the south, and you have drawn it with respect to the North Pole, remember to draw a diagram like this, so that if you ever have a latitude which is below the equator and one latitude is above the equator and you have drawn it with respect to the North Pole, you will add the value of the latitude instead of subtracting it from 90. Alright, hopefully we'll do an example and then that becomes clear to you. Alright, now that you have this figured out, we'll solve the three triangles. Let's solve triangle number 1, that is APW, and then we can solve triangle PBV. Alright, and then we'll solve this third triangle here. Alright, maybe I can just change these names because V comes before W, so let me call this V and let me call this W so that there is no confusion. Alright, VW, so PAV and PBW. So let's solve triangle PAV, and we will use Napier's rules. Why? Because if an angle is 90 degrees in any triangle, in a spherical triangle, if it is 90 degrees, this is not a plane triangle, this is a spherical triangle. If we have a 90-degree angle in a spherical triangle, we can use Napier's rules. Alright, what is Napier's rules? Let me show you. So we have a triangle like this, right? So this is P, this is V, and this is A. This is 90 degrees. PV is 45 degrees. PA is 52 degrees 12 minutes. So how can you draw a Napier's diagram? Just draw a circle. See, got to be smart about this, isn't it? So I draw a circle, divide it into two semicircles. The top semicircle divided into two halves and the bottom semicircle divided into three. Alright, write the 90-degree angle outside the triangle, or rather outside the diagram. V equals 90 degree. Alright, now what are the sides next to the angle V? What are the sides next to the angle V? We have AV and we have PV. Now what is the angle opposite to AV? Is P. So anything you write in the bottom semicircle, you will add a 90 minus to it. So the angle opposite to AV is angle P, so you will write 90 minus P. The angle opposite to PV is A, so you will write 90 minus A. And then the remaining side, which is 90 minus PA, and also the side opposite to the vertex. Alright, so you write the vertex outside the circle, V equals 90 degrees. Then in the top semicircle, you can write the sides next to it, AV and PV. You can write them in any order, but once you write them, then the order is fixed. So we've got AV and PV here. You could have written PV on the left and AV on the right, doesn't matter. But once you do that, then the order is set. So AV opposite to AV is angle P, so 90 minus P. Opposite to PV is 90 minus A, and then the remaining side 90 minus PA, which is the side opposite to the vertex. Alright, anything you write in the bottom semicircle should be suffixed with, or rather not prefixed with a 90 minus. You write 90 minus only in the bottom semicircle. Alright, so in the first instance, we will find out two things. We will find out AV, and then I'll tell you list what we have to find out. And what is given to us? We have PV given to us and PA given to us. Alright. So there are two rules to be followed in this case, rule of cos and rule of tan. Alright, so we have cos of opposites and tan of adjacents. So when you are here in this situation, you know the two things that are given to you, and the one thing that you have to find out, you can draw a mushroom which links the three values. So you draw a mushroom in a way that links the three values. So A, 90 minus A and 90 minus P is not included here. So we are trying to find out AV using the values which is given to us, PV and 90 minus PA. And we have to form an equation. So in this case, we will use the equation of opposites, because the equation we form is sine of 90 minus PA equals cos of opposite. What is opposite to 90 minus PA? Cos of AV and cos of PV. Alright, so we have to form an equation which has all the three values. In this case, we will use the cos of opposites, and I will show you what is the next equation when we come to it. So here, sine of 90 minus PA can also be written as cos of PA. That is a relationship that sine 90 minus theta has with cos theta, or cos 90 minus theta has with sine theta. It's the same. So sine 90 minus PA can become cos PA, and then we have cos AV and cos PV. Cos PV is my unknown, or rather AV is my unknown, sorry, PV I know. So AV is my unknown, and PV in PA is available to me. So I will take this to the other side. Cos of AV is isolated as the unknown, and this becomes cos of PA divided by cos of PV. So cos of AV is the unknown equals cos of PA, which is nothing but 52 degrees 12 minutes, and cos of 45 degrees, which is PV. This equals 0.86678. Shift cos inverse. So AV cos of inverse of 0.86678 gives me AV equals to 29.91 degrees. But AV, as you can see in the diagram above here, I need this as a distance. This has to be a distance, right? So how can I find out? So if I just multiply it by 60, I get it as a distance, 1794.8 miles or minutes, whatever. You might also get this as 29 degrees 54.8. That's fine as well. It's up to you. But at the end of the day, I want AV as a distance. The degrees don't make a difference here. Alright, once I've found out AV, I know AV, but I will not use AV to find my other values. Why is that? Because if I have made a mistake in finding AV, I don't want to carry the mistake forward. So next that I have to find out is angle P, but I will still use PV and 90 minus PA, the original values that I had. And again I will draw a mushroom in a way that connects these three. So these three are connected in a adjacent, they are all adjacent to each other. So I will use the rule of adjacents. So what will be the rule here? Sine of 90 minus P equals tan of PV. Let me go back to the diagram. And tan of 90 minus PA. Again, sine 90 minus P can be written as cos P, and tan PV is of course 45 degrees, and this becomes tan of 90 minus PA. PA is nothing but 52 degrees 12 minutes. So this is tan 45 times tan of 37 degrees 48 minutes, or P, and I will call it P1. Why? Because this P is not the whole angle P. Let me show you. Let me go back and show you. This will be 39 degrees and 8 minutes. Sorry, if you want me to solve further, I can solve further, but let me just let me go step by step so that you guys are not lost. So this is cos P equals tan 45. So tan of 45 degrees multiplied by tan of 37 degrees 48 minutes, which will be 0.77568. Shift cos inverse, which will give me P equals 39 degrees 8 minutes. Now why am I calling it P1 in this case? Is because this angle P refers to the angle P in triangle PAV only, not the big triangle. Alright, so in the big triangle we have angle P which is equal to 96 degrees and 20 minutes. Yes, which you found out as the D long. Now P1, I have found out the value as 39 degrees 8 minutes. 39 degrees 8 minutes. Alright, that's the only two values I have to find out. Now let me find out similar values for triangle PBV. Alright, so you start off and I will join you. So how would you go about it? Triangle PB, not PBW, sorry, the W is got erased. PBW. Alright, so draw triangle PBW. I'll use a different color pen. So this is how it looks like currently. PBW. This is the 90 degree angle. This is 45 degrees. PB is 54 degrees 20 minutes. Alright. So remember how we draw the Napiers. We draw a circle. Top circle divided into 2 halves. Bottom semicircle divided into 3 halves. Put the 90 degree angle outside the circle. So W equals 90 degrees. The sides next to the 90 degree angle will be PW and BW, or you can write BW, PW, but once you do that, the order is set now. So now if I have written PW first, the angle opposite to PW is 90 minus B, and the angle opposite to BW is 90 minus P. And finally, the side opposite to the vertex is 90 minus PB. What do I have available? 90 minus PB, because I know the value of PB, and also PW, which is 45 degrees. And what is the first thing I will find out is BW. Alright, so let me find out BW first, and then we will use the... So how can I draw a mushroom which connects these three? So it will become the rule of opposites. So sine of 90 minus PB, which becomes the middle part, equals tan of adjacents, which is tan of PW. Sorry, not tan, sorry, cos of opposites. So sine of 90 minus PB is the middle part, and then we have cos of PW and cos of BW. Now remember, sine 90 minus PB is also equal to cos PB. That's the rule. And cos PW and BW remain the same. But I don't know BW, so I will leave it on one side. I will isolate it on the left side, and I will take this to the other side. Multiplication becomes division, so cos of PB divided by cos of PW. So cos of PB is cos of 54 degrees 20 minutes, and cos of PW is cos of 45 degrees. So let's just put this value in the calculator so that you guys can compare your answers with me. So cos of 54 degrees 20 minutes divided by cos of 45 degrees is what? 0.82458. Shift cos inverse, I will get BW as 34 degrees 27.2 minutes or 34.45 degrees, up to you. But I need BW in nautical miles, so I will multiply it by 60 and I will get 2067.2 nautical miles. Alright, once I found out BW, now I can find out angle P. So remember, not angle P1, but this is now going to be P2. I'm going to call it P2 so that I don't get confused, right? So I will not use BW, although I found out BW. I will draw a mushroom that connects the unknown to the ones that I know. So 90 minus P becomes the middle part, and tan of adjacence is tan of PW and tan of 90 minus PB. So remember, this P here will now be called P2. I'll tell you why we are finding out angle P's as well. So the new will be sine of 90 minus P equals tan of adjacence, tan of PW multiplied by tan of 90 minus PB. This becomes cos P, or we can call it cos P2 in this case. This is still tan of PW, or tan 45 degrees multiplied by tan of 90 minus PB. PB was 54 degrees 20 minutes. So this can become tan of 45 degrees multiplied by tan of 35 degrees 40 minutes. So cos of P2 equals tan 45 multiplied by tan of 35 degrees 40 minutes, 0.71769, or P2 equals 44 degrees 8.1 minute. Alright, now I know that I have found out P1 and P2. If I go back to this triangle here, I have found out P1 and P2. So P2 is 44 degrees 8.1 minute. Now angle P in totality is 96 degrees 20 minutes. And I have found out P1 and P2. That means if I want to find out this angle here, P3, which is the D long between my two vertex, I can do that, right? So if I know total angle P equals P1 plus P2 plus P3, right? Now P is 96 degrees 20 minutes and P1 is 39 degrees 8 minutes. P2 was 44 degrees 8.1 minute, and P3, which is the D long between the two vertex, is something I don't know. So simply I will keep P3 on one side and I will subtract 96 degrees 20 minutes minus 39 degrees 8 minutes plus 44 degrees 8.1 minute, or you can add them up together on one side and then transfer it. So this becomes, P3 becomes 13 degrees 3.9 minutes. Now this is D long in degrees and minutes. I will convert it into minutes. So 13 degrees 3.9 minutes becomes multiplied by 60. This is also the D long between V and W. So when I multiply it by 60 to convert it into minutes, I get 783.9 minutes. Alright, now what have we learned in plain sailing, or rather parallel sailing, is that if I want to calculate the east-west distance between two positions, in this case V and W, this is called departure. What is the formula? Departure equals D long, which is P3 in this case in minutes, multiplied by cos of latitude. Latitude is 45 degrees, right? So I had to find the d long between vertices. So d long, or departure in this case, and this case departure is vw, equals d long, which is nothing but p3 in minutes. Because I need the d long between v and w, that's why I calculated p3, multiplied by cos of latitude, which is 45 degrees, which is the limiting latitude in this case. Right, so this will give me d long 783.9 in minutes, multiplied by cos of 45 degrees, and I get 554.3 nautical miles VW. Now because I have found out all three distances, so I have found out AV, I have found out BW, and I have found out VW. If I add the three together, I can find out my total distance from A to B. So in composite great circle sailing, we only find out total distance. So in this case, AB will be equal to AV plus BW plus VW. So in this case, I will add 1794.8 plus 2067.2 plus 554.3, which is total 4416.3 nautical miles. That is my great circle distance, or composite great circle distance. That is my answer. Alright, so the video is long enough now. Watch this video slowly, pause it where required, watch it again, keep watching it till you get the concept, and I will make another video. I'll take up a different kind of a question on composite great circle sailing and upload it for you guys soon. Bye for now. See you.